The Louis Burke Frumkes Center for Writing and Culture at Hunter College presents 10 years of best-selling authors and great thinkers.
It gives me great pleasure, ladies and gentlemen, to welcome Caleb to Hunter College this evening to speak to you on some of these very profound and fascinating subjects and perhaps illuminate them for you. Caleb?
Let me just retrieve a microphone. Thank you. I have this because I know I walk around a lot. My students always tell me that if only I would stand still for a moment, but I'm afraid I can't, so I'm not even going to fight it. So thank you very, very much for that introduction. It's a pleasure to be here this evening on a beautiful, warm April day, April evening. What I thought I'd do for the next 40 minutes or so is talk to you about some of the deepest questions that we ask of our place in the universe, about the nature of our existence, and about our importance or not in the grander scheme of things. These are questions we've been asking for a very, very long time as a species, and I want to try to dig into those a little bit and perhaps show you that we, on the one hand, are getting awfully close, perhaps, to having some real answers, but at the same time, there are some big unknowns and problems. And part of the problem is we have this complex. And the complex, it's the Copernicus complex, but it's also to do with this. It's to do with the question of our significance or insignificance in the grand scheme of things. And I thought I'd begin by just trying to illustrate that very briefly in almost a pictorial way. So let's think about cosmic significance. What better place to begin than with me? So this is a picture of me when I was about a year old, and we'll start here. So I was born here, which is a city you might be able to recognize from the picture. It is a city that exists on a modest island on one side of a great ocean on this planet that we call the Earth, which is a ball of rock and iron covered in a thin veneer of atmosphere and water. And the Earth is not alone in the universe. The Earth has a companion, the moon, shown here in correct proportion. And around the time that picture of me was taken, I can't quite believe I'm admitting this because it means I'm much older than I think I am, humans, for the very first time, went from there to there, came back again. Total round trip of about 500,000 miles. And in retrospect, it's perhaps not so very surprising that that is all that we did, because all of that exists in that little point of light down there. This is the Earth and the Moon at a distance of 93 million miles from a fairly ordinary star that we call the Sun. And the Sun is, of course, merely one of some 200 billion stars in a great swirl of matter that we call the Milky Way galaxy. And the Milky Way galaxy is not the only galaxy in the universe. It exists in a small grouping of galaxies, and these galaxies are not the only galaxies in the universe either. They're in fact just some out of some 200 to 400 billion galaxies in the observable universe. The observable universe is the universe from which light has had time to reach us in the last 13.7 to 13.8 billion years. We have been mapping this universe out over the last few decades to the extent that we can construct maps like this. In this map of part of the universe, each tiny little speck of light there corresponds to an entire galaxy of stars. If we could complete this map to the edge of that observable universe, it might look something like this. And we now have some reason to believe that this may not be the only observable universe, that there may be other universe-like things separated in space, time, or dimension. In fact, if you talk to theoretical physicists, some of them will tell you that the total number of distinguishable universes is about 10 to the 10 to the 16. And that is the number of universes that can be discriminated between, that are information carrying capacity the human brain is capable of distinguishing. There could actually be 10 to the 10 to the 10 to the 7 other universe-like things out there. So, after all of that, are we at all significant? Are we special or unique? You might agree that these seem to be rather ridiculous questions to be asking at all, because clearly the answer is no. But that there is the crux of it. In the face of the enormity of reality, one is inclined to say, well, me and my little pram in a park in London, I'm not significant. I can't possibly be important to the universe as a whole. You know, whether I'm special or unique, maybe, you know, possibly that's something we have to deal with, something we have to address. And the interesting thing about this is that it really all comes from people like Copernicus. This picture of the universe that we have today is in part because we now have the capability of mapping out the cosmos around us, but it's also because when Copernicus thought about the structure of the universe as he knew it, which was very, very limited, it was really the solar system that he was talking about, when he posited that it was the Earth, or rather that the Earth was not the center of all existence, that it was the sun in our solar system that was the center of existence, he set in motion this idea that, well, we don't necessarily occupy a particularly important or special place in the cosmos. And over the years, that has been a centrally important idea. It was very important for Newton. It was important for Einstein. It was, in fact, embedded in Einstein's mathematical physics description of the universe, that there is no preferred center. There is no special place in the universe. And it's given rise to what I call the principle of cosmic mediocrity. Okay? And that, in simple terms, is that the circumstances of the Earth and life on Earth are not special in any way. Not special, not significant. And it makes a great deal of sense, this principle of cosmic mediocrity. But one thing that is interesting, if you take this to its logical conclusion, is that therefore life should be everywhere. Because if we're mediocre, then there must be lots of other things out there. There must be lots of other mediocre life in the universe. Otherwise, it'd be something special, something central about us. So one of the logical extensions of a principle of cosmic mediocrity is that there has to be life everywhere. Well, okay, that's not so bad. We don't know the answer to that yet. I'll talk a little bit more about that shortly. But it's not so bad. Except there are some cracks in this picture. There are some little cracks in this picture of cosmic mediocrity, and I'd like to talk about those, and we'll see where we get to as we go through this. So the first crack in that picture is actually really due to physics or due to cosmology, our understanding of the nature of the universe and the functioning of the universe. Because in the 20th century, we first discovered that the universe has a finite age. Okay, that was news. The universe has not been around forever. In fact, we now know it's been around for about 13.7, 13.8 billion years, following the event we call the Big Bang. But not only that, a number of physicists in the 20th century began to notice that there are certain characteristics of the universe, certain fundamental properties, and I'll show you some of those in a moment, that are independent of each other and are not, at this point, determined by any particular theory. They are just what they are. But if you changed any of them a little bit, you would subvert the entire pathway to life. So in that sense, the universe seems to be really tuned to give rise to life. In other words, the existence of life is itself perhaps telling you something about the fundamental properties of the universe, which is very, very strange, and certainly not part of the Copernican view of mediocrity. So let me put up a list, and this, please don't let this cause panic for those of you who are not scientists. Okay, this is a nasty looking list of fundamental properties of the universe. It's about 6 things here. So I'll just describe a couple of them. So these are these qualities of the universe, these physical properties of the universe that are independent of each other, essentially, and take very specific values that if you change them a little bit, you would alter the universe quite radically in such a way that life probably couldn't exist. So for example, the first one, this thing, the ratio of the strength of gravity to electromagnetic forces. What does that mean? Well, it's just, gravity is a force, electromagnetism is another force, and there's a particular relative strength, and that, in this case, is particularly important for the existence of these things we call stars. So stars are essentially a standoff between gravity and electromagnetic forces. And if you change that ratio a little bit, you might not make stars in the universe. And if you don't make stars in the universe, that's kind of problematic for life as we know it, because you don't make all the heavy elements. Stars build heavy elements. They build the carbon, the oxygen, the nitrogen, and so on, that are in complex molecular structures that lead to stuff like us. So if you don't have stars, you don't have all of that. And the same is true of the second one, the percentage of matter converted to energy by the fusion of hydrogen into helium. Well, that's to do with processes taking place in the cores of stars and the production of those elements. And you go down this list, and so there are things like energy density of quantum vacuum fluctuations, which sounds very scary, and it probably is. But if you change that a little bit, the universe would not be the same. So the bottom line is that all of these things have to apparently line up just right for life to occur, and life does exist. And so there's something funny going on here. It's saying that life is somehow special. Now, if you didn't go to the pub before coming to the talk, you're probably sitting there thinking to yourself, but that's kind of stupid, right? Because look, if it weren't like this, we wouldn't be here to make that observation. So it's only natural that the universe is kind of tuned like this, right? Because otherwise we wouldn't be here to make the observation. And that's absolutely true and perfectly rational. So, I mean, actually, maybe you would have come to that conclusion if you had been to the pub. In fact, a lot of physics is a lot easier if you go to the pub first. Or at least it seems easier. So that's interesting, but here's the problem. If this is the only universe, if this is the once and only universe, why did it turn out this way? It is true that if it hadn't turned out this way, we wouldn't be here to observe it, but why did it turn out this way? That's very disquieting, and it makes a lot of physicists and other scientists kind of uncomfortable to say that there really is something special going on here. Well, so there is a possible answer to this, and it goes back to something I mentioned a couple of slides ago, which is maybe this isn't the only universe. Maybe this isn't the totality of reality. It's just a tiny piece of a multiverse of 10 to the 10 to the 16 other realities, in which case they all have different sorts of properties. And some of them will be suitable for life and some won't. So it's only natural that we find ourselves in one of those 10 to the 10 to the 16 universes that is capable of producing life. Problem solved. You just have to evoke the existence of 10 to the 10 to the 16 other universes. It's easy, right? You do that before or after going to the pub. So maybe that is a solution. It's a pretty big, bold thing to say to solve this problem, but maybe that is a solution. But what I would say about that is it's still kind of tricky because, first of all, it doesn't require anything more than the existence of life in one single place in the entire universe to have to try to answer these puzzles, right? We could be totally alone in the universe and you'd still be twisting yourself into a knot to make this chain of logic that doesn't evoke something special about life or the universe. And we don't know if we're the only life in the universe. And it also doesn't really, for me, it doesn't really satisfy the urge to understand our true significance. I mean, where do we stand just within this universe, never mind the possible multiverse? And that's something that we can do something about. That is something we can tackle. And so let me say a little bit about that. And what I'll tell you about now is it's central to answering questions about the existence of other life in the universe. We think that planets, particular planets that are somewhat like the Earth, are kind of special in the universe only in the sense that they are capable of harboring environments where complex chemistry can take place. They're not too hot, not too cold, they have the right mixture of elements. There are very few other environments in the universe, places between the stars and so on, that can do all of this. So planets are important. But 20 years ago, we didn't know if there were any other planets around other stars. We didn't know of other solar systems. We only knew of our own. Now, we might have expected and anticipated that there should be other solar systems. Certainly, the principle of cosmic mediocrity would tell you that there should be other solar systems. But we didn't know for sure. And what's happened in the last 20 years is there's a number of technological breakthroughs and advances, and really a revolution in astronomical science. Because we now know that planets do exist around other stars. In fact, since the early 1990s to today, we've now detected more than 4,000 candidate planets around other stars. And some of the technology includes things like this. It's just an animation of a launch of NASA's space telescope called Kepler, that over a period of years monitored the light coming from about 150,000 stars, looking for tiny changes in the light from the stars because of planets orbiting around them and coming between us and the parent star and blocking a little bit of the light. It's a bit like looking at moths flying around a lamp on the porch and detecting that tiny diminution in light, and it can reveal the existence of planets. So Kepler has been incredibly important for this. So much so that we now have headlines like this in the New York Times: far-off planets like the Earth dot the galaxy. And for once, the headline is accurate. Well, I should be careful. Dennis Overby wrote this, and he's usually right. He's usually accurate. So far-off planets like the Earth dot the galaxy. We now know that planets are incredibly abundant. Pretty much every star, at least in our galaxy, has some planets around it, which is remarkable. It need not have been that way, but it is. And the statistics are so good now that we can make statements like this. We can say that within 20 light years of the Earth, so a light year is 6 trillion miles, I think, so within a mere 120 trillion miles, which may sound like a lot to us, but on a cosmic scale, that's a tiny drop in the ocean. We're confident that within 20 light years of the sun, there should be another star with at least one planet that is a candidate Earth analog, a planet of similar size to the Earth, orbiting its star at a distance where the surface conditions could be amenable for complex chemistry, could resemble those of the Earth, the modern Earth in some respects. And that also means that within our galaxy, that swirl of 200 billion or so stars, there should be at least 15 billion Earth analog planets out there. Now, we don't know what's on those planets. We don't know exactly what their conditions are. That's part of the thing we're trying to find out. Many astronomers and scientists are trying to find out is what really are the conditions on those planets. All of this changes a lot for these questions of cosmic significance or insignificance. And let me show you one example of that. So now we have these catalogs of other worlds, these catalogs of other solar systems. We can ask and answer some questions that we've never been able to tackle before. And here's one example. It sounds very simple. How does the solar system stack up against others? So for the first time in human history, we can now ask, not just in general terms, but in specific quantitative terms, how different our solar system is from all the other solar systems. Are we ordinary, or are we somewhat unusual? And I'll show you some of the ways we do this. It gets, of course, increasingly technical, but for example, we can look at the architecture of our solar system. By that, I mean the shape of the orbits, the distribution of the orbits of the planets and the distribution of the sizes of the planets. We can also look at the stability of our planetary system. So this is a dirty little secret, or maybe it's not such a secret, but planetary systems tend not to be perfect. They tend to be chaotic. Our own solar system is actually chaotic over timescales of hundreds of millions to billions of years. But we're not as chaotic as other planetary systems. So between the various measures of the architecture of our planetary system and its stability, we're kind of like a 1 in 4 place. We're in a sort of 25% club compared to all the other planetary systems out there. So that's sort of interesting. It's not earth-shattering, but it's kind of interesting. We can also look at the types of planets. So we don't have one of these planets that's called super-Earth. So a super-Earth is a type of planet that we hadn't seen before. It's something that is more massive than the Earth, but not as big as the planet Neptune in our own solar system. And it's a very interesting category of planet. Does not exist, at least within the inner solar system of our system. And that puts us into a sort of 40% club, because there are lots of super-Earths out there around other stars. And the list goes on. So for example, we can look at the type of star we're orbiting. And this one always strikes me as interesting, because it's so obvious in retrospect, but we just hadn't really looked at this question this way. So the majority of stars in our galaxy, and probably in the universe as a whole, are not like the sun. They're actually smaller. They're less massive. In fact, in our galaxy, 75% of all stars are less than half the mass of our sun. And they have planets around them. And so the fact that we don't orbit a star like that puts us in a roughly 10% club. And so on and so on. We can add other factors. For example, we have this planet that we happen to be sitting on or standing on right now that's in the so-called habitable zone. It's at that sort of sweet spot in terms of distance from its parent star, where the surface environment can be temperate, can be suitable for complex chemistry. You put all of these things together and other factors, and the bottom line, and this is kind of conservative, but the bottom line is that our solar system is kind of a 1 in 100 type place by comparison to everything else that's out there. And that's interesting. So it's somewhat unusual. It's not extraordinarily unusual, we think, but it's somewhat unusual. And whenever we see something like that, we have to ask the question, is there a connection between that degree of unusualness and the existence of life here? Is it the case that only these 1 in 100 type solar systems give rise to life? Now, to answer that question, we of course need to know what the impact of these various properties of the solar system are on the origins of life here. We don't know what the origins of life really were. That's an active area of research. We don't understand where life comes from completely. So it's very intriguing. And that leads me to another intriguing observation. And again, these are all sort of cracks in that idea of cosmic mediocrity. Right? They're all things saying, well, maybe there is something a little bit special or unusual about here. So there's another argument. And what I'm going to do is I'll explain what this argument is, and then I'm going to try to tear it to shreds, which is always kind of fun. It's a scientific method. Okay, someone once said to me, yeah, scientists are the most brutal crowd you can possibly have because they'll smile at you and tear your ideas to pieces. And that's a good thing. So along this line of asking whether or not there's something unusual about the Earth, about life on Earth, is an argument that's been around for a while, and it's often called the rare Earth argument. And I'll explain what it is, and then I'll try to show you why it may be completely wrong. I would use an expletive there, but I'm in polite company, so I won't do that. But it's interesting. It's very interesting to think about this. So the argument is that on Earth, we have complex-celled life. We are complex-celled life. We are large multicellular organisms, but the cells that make us up they're called eukaryotic cells. They contain quite complex structures. They are quite different in their complexity than, for example, bacteria cells. Single-celled bacterial organisms just don't have as much interesting stuff in their cellular structure, in the cells. Complex-celled life is something a bit different and is clearly the result of further evolution at a cellular level. And the argument goes that complex-celled life is kind of unlikely anywhere, here on Earth and across the universe. And that argument goes along lines of looking at the history of the Earth and the history of life on Earth. So for example, we are a planet with that moon. We have a large moon. And that moon is the result, we think, of essentially random processes in the very young solar system. It originated, we think, from a giant collision between protoplanetary objects 4.5 billion years ago. But the existence of the moon is interesting because the existence of the moon helps prevent the spin axis of the Earth, the poles of the Earth, from moving too much over time. If you took the moon away, there are subtle gravitational interactions between the Earth and the Earth's spin and planets like Jupiter and Saturn that would make the pole of the Earth change dramatically by 50 or 60 degrees over a few tens of thousands of years. And that would destabilize the climate of the planet. So the existence of the moon helps maintain a more stable climate over geological timescales. And the more stable climate, we think, is more suitable for complex life. And there are other things, the particular mix of water and dry land that we have on the Earth, again, helps stabilize our climate long term and may be more conducive to the sort of chemical energy sources that complex life likes to make use of. And we know that the history of the evolution of life on Earth has been subject to all sorts of extinction events. So, for example, if a big asteroid comes in, hits the Earth, and wipes out most of the life on the planet, that sounds kind of sad, but it actually creates opportunities for the life that survives to evolve into new forms. So, but it's a random process, or essentially random process. So our history has all these contingencies in it. And perhaps the biggest one, or the most striking argument, this image may be totally uninformative. What it's meant to show is mitochondria inside a cell, inside a complex cell. So our cells, like all complex-celled life and pretty much all multicellular life, contain these structures called mitochondria, which some biologists argue, very convincingly, are the result of an extremely unlikely merger of two simpler organisms some 2 billion years ago, give or take a few 100 million years. I mean, astronomers are terrible at numbers. But way back in evolutionary history, an extremely unlikely merger and eventual symbiosis of two simpler organisms could have caused these mitochondria in our cells. And mitochondria are interesting because they are power sources, like superchargers for cellular energy. Okay, the existence of mitochondria in our cells allow us to express something like 200,000 times more genes than a bacterium can. It's because we have more chemical energy. But if that hadn't happened 2 billion years ago, we wouldn't be here. So the rare earth argument is if you take all of these quite unlikely things that had to have lined up in history in order for us to be here, it means that this cannot have happened many other times in the entire universe, if at all. Okay, that's interesting. That's a real count in principle against the cosmic mediocrity idea. So now let me argue why this is probably wrong, or could be wrong. And it's to do with probabilities and interpretations of probabilities. It's to do with what I call the inevitability of the improbable. Okay, so I'm going to have to do this by telling you a little story. Okay, and it's a story about baseball. So you probably weren't expecting this, right? Baseball in a talk on science and life in the universe, but it'll work. So this is a picture of a baseball stadium. It's actually in Japan, where baseball is an extremely popular sport. It was the first picture that Google gave me, so I thought, fine. So here's the story. So imagine I'm sitting at home one morning. Unusually, I'm not usually sitting at home one morning, but I am, and the phone rings, and instead of ignoring it, I actually pick the phone up. And on the other end of the line is a long-lost friend from 20 years ago, someone who's found me. It's wonderful. We have this great conversation. And they say to me, you know what, I happen to be in town. Not only that, but I have a couple of tickets to this fantastic baseball game later today. Do you want to go? Sure. So later on, they drive by and they pick me up and we head towards the stadium, except there's a lot of traffic, and so we get stuck and we have to take a different route. And we get to the stadium and we have to park in the wrong place, and we have to walk into the stadium and walk through the crowds to try to get to our assigned seats. And as we're walking through the crowds to get to our assigned seats, a great batter comes up on the field. We decide in the spur of the moment, you know what, let's just stop and watch. So we stop, we watch, the ball is pitched, the batter hits it, it sails up in the air, and it lands in my hand. Well, that's not me. That's some poor surrogate in this picture. But so the ball lands in my hand, and I stand there thinking to myself, that's incredible, right? If I hadn't been at home this morning, if my friend hadn't found me, hadn't called me, I hadn't picked up the phone, if they didn't have tickets, if we didn't get stuck in traffic, if we hadn't been walking through the crowd at that very instant and stopped just then, I wouldn't have caught the ball. How unlikely is that? It's incredibly unlikely. Except it depends on your perspective. Because in a stadium of 50,000 people and great players, during the course of the game, it's basically inevitable that somebody is going to catch a ball. Probability 1. But whoever catches the ball will be asking themselves exactly the same kinds of questions. There'll be different questions, but they'll be the same thing. They'll be thinking, wow, how lucky is that? If I hadn't fallen out of bed this morning, if I hadn't flushed my cell phone down the toilet, if I hadn't tripped over a black cat, et cetera, I wouldn't be here at this instant putting a hot dog in my mouth when the ball comes in and lands in my hand. Right? So it's a very interesting situation because this was going to happen to someone, and whoever it happened to would be thinking that they were very special, that this was just this rare thing. Now, by analogy, the situation of asking about the rarity of complex life on Earth is that it's kind of like being in this stadium but not knowing who else is there and catching the ball. If you don't know who else is there, you're going to say, that is incredibly unlikely, right? This could not happen again. But you don't know that there are 50,000 other people in the stadium. And we're very bad at this sort of probability. We're very bad at this sort of interpretation. Right? And it's all about how facts take on new meaning after the event. Right? We begin to assign meaning to things in retrospect in order to explain what has happened. And so the point of that is, let's suppose that we live in a universe where complex life is rare, as the rare earth argument goes. Well, that complex life is going to be sitting around in the pub, and it's going to be saying, I think we're rare. We're very, very unlikely. I'll have another beer. But suppose we live in a universe where complex life is actually very common. If it doesn't know any better, it's going to be sitting around going, well, I think we're very, very rare. I'll have another beer. Okay? Without additional information, in both cases, you're going to come to the same conclusion. Now, that doesn't mean that the rare earth idea is wrong, but it means that it could easily be wrong. And that there could be many other pathways, historical pathways of evolution and chance that lead to basically the same kind of conclusion, the same catching of the baseball at the end. It's just going to be different each time. So I'm getting towards the end here. So what do we do with all of this? It's kind of tricky, but it's so tempting to try to make a conclusion from all of this. And this is, I've only talked a little bit about some of the evidence and some of the scientific findings that are relevant to this. To learn about the rest of it, you have to buy the book. But let me share, I think, one of the conclusions or one of the possibilities. So I think there is at this stage, there is a reasonably logical solution to this conundrum between things being special, because there is evidence of things being special. And although I'm dismissive of the rare earth idea with the baseball analogy, I can't really prove that it's wrong just yet. But there's this conundrum between special and mediocre, evidence for special and evidence for mediocrity of our existence. Well, as unique or as special as we are, there seems to be vast potential in the universe for other equally special planets and life to emerge. We know there are lots of other planets out there, at least 15 billion in our own galaxy that could conceivably resemble the Earth in some way. And again, I didn't go into this tonight, but our understanding of the fundamental nature of biochemistry and carbon chemistry suggests that it's ubiquitous, that it's everywhere in the universe. So one answer to this, and it may sound kind of trivial in the end, but a logical conclusion to this is that we're special but not exceptional, or unique but not significant. In other words, we may be surrounded by other life in this universe that is all equally unique. Right? It's different than us, but there's lots of it. That would solve this problem. That would solve this logical problem. This would solve this conundrum. Okay, so I have a couple more slides to go. So, what are we doing to really answer this? Well, a lot of people are working on this, and a lot of people are taking what we've learned about planets around other stars and our ability to explore the universe around us, myself included. And right now, it's a hot topic. So we are, as I'm sure you know, actively exploring Mars to look to see whether there is life there today or whether there ever has been life on Mars. And finding an example of life that originated separately from us would be tremendously important. It would completely change the statistics about how likely life is elsewhere in the universe. Because right now we only have the sample of one. If we have 2 data points, we can do an awful lot more. We're also studying other places in our solar system. These are icy moons around the giant planets, Jupiter and Saturn. This lower picture here is Enceladus, which is a small icy moon around Saturn that has active cryovolcanism. We think, in fact, we're very sure that it has an interior ocean. It has a deep ocean of liquid water beneath an icy crust, and that liquid water seems to probably have been in contact with hydrothermal systems, hot rock at the bottom of that ocean, much like happens in our own Earth's oceans. And those are places where life exists, and some people have posited could be places where life originated. We're also beginning to learn how to look for the signs of life by using telescopes to sense the chemical composition of atmospheres of some of these potentially Earth-analog planets out there, looking for so-called biomarkers, gases like oxygen and methane and carbon dioxide and water and so on, which may give us a hint as to whether or not there is a biosphere in one of these distant worlds. And there's been a resurgence of interest in the search for extraterrestrial intelligence, or SETI. And this is something that has gotten an unfairly bad rap over the years, but in part that's because it's a strange scientific challenge. You know, you could listen forever with the most sophisticated equipment, and maybe you'll never hear the signs of intelligent civilization out there. What does that even mean? How do we know that another form of intelligence or civilization will do the things that we do? We don't. But if it does, we'd really like to catch it. We'd really like to detect it. So people are getting back to this, and they're looking for radio signals. They're looking for structured, visible light signals coming from around distant stars, or even quite seriously looking for so-called artifact SETI, artifact search for extraterrestrial intelligence, whether those are big structures that some civilization has built around a distant star, or other things that have been strewn about the universe that would give away the existence of other intelligent life. So this is all wonderful and it's exciting. But now let me just take it one step further and extrapolate this and ask, well, what's the ultimate goal of all of that? Yes, okay, we start to discover that there's other life in the universe. That's wonderful. But let's think even further down the line. And this kind of comes full circle to what I spoke about at the beginning, to do with many realities, many universes. What if, not just detecting other life in the universe, but we could actually measure the abundance of life in the universe? So what do I mean by that? Well, look, the universe, the observable universe, the universe from which light has had time to reach us in the last 13.7 billion years, is essentially a finite thing. It's got those 200 to 400 billion galaxies in it. What if we could measure exactly how much life there is in that observable universe? It's a number, right? You know, I don't know how you do it. Maybe it's number of cells or number of planets with life or something like that. It would tell you the fertility of this universe. And if you could figure out what drives that number, what drives the amount of life in the universe, and presumably relate it to the fundamental properties of the universe, then conceivably, this is really crazy, wild stuff, but it's probably not going to happen for another 1,000 years, but what the hell, we'll talk about it anyway. You could perhaps evaluate the true significance of life in the totality of all possible realities. You could compute how much life there has to be across the multiverse of 10 to the 10 to the 16 universes. Now, maybe you'd be a little tired before you got there and would do it, but you could in principle, and that's kind of an interesting thing. What would that tell you? We don't know, but it would be fascinating. Okay. And on to the last slide, which I think is good timing, so that there's questions, time for questions. I'm going to end by stepping back from all of this just a little bit. These questions of cosmic significance, of whether we're special or not, whether the cosmic mediocrity holds, are all very interesting and important. But there's something else too going on here, something that is kind of peculiar. And I'll argue that there's another, perhaps even simpler option available to us in this quest to determine our significance, which is that we don't have to be satisfied with the answer we get. We have the option to change the equation. And like it or not, we've actually already started doing that. So this is an animation of the Voyager 1 spacecraft. It was launched in 1977. It is still active. It's now about 130 times further from the sun than the Earth is, about 12 billion miles or so away from us, and it's heading out into interstellar space. In a few tens of thousands of years, it will pass relatively close to some other stars. It may well outlive biologically modern humans as a species. It may be a relic of us. It may be an imprint that we have made on the cosmos. And that's interesting. That changes our significance. And in principle, it's not just our robotic avatars that we could send out into the universe. It's us. We don't quite know how to do it. And in the news yet last week was discussion of sending probes to Alpha Centauri. It's very, very difficult. And that's going to be an interesting project to see unfold over the coming decades. But in principle, we could do it. And that, you know, is perhaps something that makes us special. We have this capacity to extend ourselves, to make ourselves significant in the cosmos. And I'll stop there. Thank you very much.
Thank you very much, Caleb. I'm sure everyone found that interesting.